Good evening, distinguished guests and participants. First, I want to extend my gratitude to Professor Kalok of ASEAN University, Taiwan, for inviting me to deliver a speech in this seminar. This talk is made possible through cooperation of ITB, IEEE Indonesia Section, and Asia University. My name is Adrian Suksmono. I am a faculty member of the School of Electrical Engineering and Informatics, Institut Teknologi Bandung, Indonesia. Today, I will deliver a talk on finding Hadamard matrices using quantum computers. The contents of today's lectures are as follows. First, introduction, which talk about the Hadamard matrices in general. Then it is followed by finding Hadamard matrices by various methods. And in the third part, I will talk about finding Hadamard matrices using quantum computing. And in section 4, I will give a brief description about the experiments. And then I will conclude this presentation in part 5. So let us start the introduction section. So what is the Hadamard matrix? By definition, it is an orthogonal binary matrices which interests are -1 and +1. And it has various applications such as for orthogonal codes in the digital communication system CDMA. It is also used in error correction code with maximal error correction capability, and it was employed in Mariner 9 spacecraft. And it is also used in the experiment design, which is explained in the Hidayat papers. And in terms of its importance in scientific and mathematics, we know that there's a conjecture called the Hadamard matrix conjecture, which is about 100 years old unsolved problem. And why finding Hadamard matrix is hard? We know that since the element of Hadamard matrix is -1 and +1, okay, so they are binary. If we have an M-order matrix, which means that we have M by M matrix, there will be 2 to the exponent of m squared, 2 to the power of m squared, and it is about exponential m squared of binary matrices. And Hadamard matrix conjecture predicts that there is a Hadamard matrix for every m multiple of 4k, where k is positive integer. The problem is how to find it. So if we are using brute force and we consider the worst case condition, then one should check all of the binary matrices, which is a big O exponent m squared problem. So this is actually a hard problem. And in this presentation, we propose to use a quantum computer to help us finding the Hadamard matrix. One of the earliest methods to construct a Hadamard matrix is by using Sylvester method. In this method, we started with 1 by 1 Hadamard matrix, each one, and then we can easily get the H2, which is 2 by 2 Hadamard matrix. Since there are only 4 entries, then we can try every possible 1 and -1, and we can normally have 1, 1, 1, -1 Hadamard matrix. And then from this we can do the Kronecker product or the tensor product of the next level order. For example, it's 4. Then we do the tensor product of H2 by H2, and so forth for the higher order Hadamard matrices. So here, if we have order 2 to the power of k, then the h2 to the power of k can be obtained by tensor product of h2 by h2 to the power of k minus 1. So the order of Sylvester-Hadamard matrices should be 1, 2, 4, 8, 16, etc. to the 2 to the power of k. And this is the limitation of the Sylvester method. It's only capable to construct the order of 2 to the power of n Hadamard matrices. So for example, for Hadamard matrix of order 12, we can use this method. And there are other methods for order 4k. For example, Paley, Baumert, Hall, Williamson. But this method, by using this method, we cannot find all of the 4k order Hadamard matrices. So for the order under 2000, we have several Hadamard potential Hadamard matrices. Actually, this is a binary matrix, but we don't know if they are Hadamard or not. So, for example, the order of 668, 716, 892, etc. up to the 1964. We don't know if these matrices are exist, or how we can describe this matrix, the form of this matrix. And we are moving to the next section about finding Hadamard matrices. We can have three different methods to find Hadamard matrix. So in the first method, we call it exhaustive method or enumeration method. The method runs as follows. So let's say we want to find an M-order Hadamard matrix. What we do is we list all possible 2 to the power of m by m binary matrices, and then do the orthogonality test to each one of them. By this way, we can ensure that we can find a Hadamard matrix if there is one, or if there is no Hadamard matrix, then we can say that in this order there is no Hadamard matrix for sure. The drawback of this method is the complexity. So we have to check all of the 2 to the power of m by m, and it belongs to the class of big O to the power of m times m, and it is exponential complexity, and therefore this is hard. The next method we call probabilistic method, and by this way we can generate random factor, then test it one by one. So we name it as random factor selection. So the stages to find such matrix can be simplified into 2 steps. First, we generate m-ordered binary matrix randomly. Then we do the orthogonality test until it passes the test. And when generating the m-ordered binary matrix, we started with one binary factor that satisfy a particular restriction, and then we generate the next vector and perform the orthogonality test of this vector, and it is continued until all of the vectors are found. And the last one will be optimization method. And in this method, we start with an n-order random binary matrix. Then we measure the error energy E, and then we can flip the entries, the element of the matrix. And if the flip make the energy reduce, then we accept. But if it makes the energy rise or increase, then we accept only by a few probability. And when the test, the transition goes to the energy 0, then we conclude that we have found the matrix. We can do this kind of optimization method by two ways. The first one is classical, and it is naturally called a simulated annealing or thermal annealing. And the second one is quantum or quantum annealing. So let's go to the enumeration method a little bit detailed. So this algorithm displayed in this PowerPoint in this screen is the detailed algorithm for exhaustive search method, and the right part, figure 3, shows a list of 4 order matrices that can be obtained by using this exhaustive method. Although we restrict only the semi-normalized Hadamard matrix, we can do in general for any kind of non-normalized matrices. The random factor selection algorithm is displayed in this screen. So in principle, we start with a vector, a corresponding vector of 4k length, and then we generate the next vector and perform the orthogonality test, and we continue until all of the vectors which are orthogonal to each other are found. In the bottom left part, we show here the found 12 order Hadamard matrix, and the right figure is the we call it the D, or the indicator matrix. The indicator matrix indicates whether the corresponding matrix orthogonal or not. So if it is orthogonal, then the main diagonal entries will be particular value. In this example, it is all 12, and 12 by 12, 144, and the off diagonal will be 0. In the right part, we show here the running process of finding such matrix, and we can observe here in the semi-logarithmic curve that when we increase the order, then the time, the steps to find the Hadamard matrix increases linearly in this semi-log plot, which means that it is actually grows exponentially. And the third algorithm that we saw here is a classical simulated annealing. And as we have explained previously, we started with a random binary matrix, and we flip randomly an element from 1 to -1, or from -1 to +1, and we do the orthogonality test. Actually, we measure the energy, and if it is goes down, if it is reduced, then we accept the transition, and if it is increased, then normally we reject, but sometimes we accept it with certain probability. So by the iteration, the energy will be reduced, although sometimes it increases, but it tends to reduce up to a certain point when this matrix is found. And the upper part of this figure shows the annealing schedule. So this screen shows some result of execution of the simulated annealing algorithm. The left upper part of the figure shows the initial stage. So this is the random binary matrix, and this is the indicator matrix. We can see here that the off-diagonal entries of this matrix are non-zero. And after we run the algorithm and we reach the energy equal to 0, then we find the orthogonal matrix, the Hadamard matrix, and its corresponding indicator matrix shows only main diagonal which are non-zero, and the rest of diagonal are all 0. And the right part shows the iteration displays as graphics and as a table. So we can see here that this this curve shows exponential growth of the complexity if we plot it against the order of the Hadamard matrix. And now we arrive at the central topics of this talk: how to find a Hadamard matrix using quantum computing methods. So the main idea of this method is exploiting the orthogonality condition of the Hadamard matrix, which is a Hadamard matrix multiplied by its transpose should be equal to identity. So let's start with a binary matrix P, and in general, P transpose multiplied by D, we will define it as D, an indicator matrix. And in general, D will not be equal to I. Then we flip elements of B, which are Bij, such that D approaching I. And finally, we hope that it will be equal to I. So let D equal Dij, and we define the error energy E as the sum of absolute values of the off-diagonal entries of D, which is E equal sigma absolute value of Dij, and specifically we will take a quadratic value of Dij and then minimize E by flipping Bij. So if we have an entry which value is 1, we flip into -1, but if we have -1, we flip into +1. So we can consider 2 by 2 Hadamard matrix or a binary matrix like this, and in the quantum solution, we will consider this element as spin, and +1 equals spin up, and -1 will be corresponding to spin down. So we can consider this spin configurations, this Cupid configuration, which initially has the energy more than 0, so they are not in the ground states in a particular sense. We evolve by the time, so it can be in this form or another forms, and eventually at the final stage they all will be equal. The energy of this configuration will be equal to 0. So for this initial states, which energy in this level, there are two ways to evolve this configuration. The first one is by thermal annealing. We already discussed this case, and in this case we discuss simulated annealing. And in the simulated annealing, this configuration should jump in above this this energy barrier. But if we use quantum annealing, then we can tunneling through this energy barrier. So eventually we hope that they will reside at the ground states, the energy equal to 0, and we can obtain the Hadamard matrix. So this binary matrix then change into this Hadamard matrix. Now let's discuss a little bit detail about the objective or energy function. First, we have a binary matrix P with element Bij, and Bij can be the value of Bij is either 0, 1 or -1 plus 1. It depends on which representation we want to use in this case. And for the first case, the initial case, we have -1 plus 1 representation. So we work in a spin variable domain. So this is the binary matrix. We name the element S0, S1, etc. And the next one will be the next column will be SM, SM plus 1, etc. And we have the last element will be SM square minus 1. Then we'll calculate the energy of this binary matrix. And after some simplification, some algebraic manipulation, we get this compact equation. So Ek in the domain of S, we also call it E4 because the highest interaction term is 4-body, will be equal to m squared multiplied by m minus 1 divided by 2 plus 2 multiplied by sigma Si, Sc, Sm, Sn. So this they are all 4-body terms. But we know that quantum annealer like D-wave only takes 2-body interaction terms at maximum. So we have to convert all of these 4 bodies interaction into at the highest will be 2-body. We can take 1 body and 2-body. And we have this formula that we adopted from a paper in a physical review, which say that a 4-body term can be converted into 2-body term by using this expression, this equation. And then we do this automatically by symbolic computing, and we can see here. But after this process, we put back this equation, the energy function, into spin variable equation. So we transform from the initial EKS into the final A2S by using this sequence from EKS to AKQ to A2Q, which is 2-body in Boolean domain, Boolean variable. Then from Boolean variable we convert into a spin variable, and finally we can get the Hamiltonian, the potential Hamiltonian or a problem Hamiltonian A2 hat, H2 hat. Again, because too many terms to do by hand, we need automatic computation, and in this case we are facilitated with Python. Yes, Python have a package that can do symbolic computing, and we can formulate the computation by using this package. Then after we have its potential, the problem Hamiltonian, we put it in this equation of quantum annealing. So in this equation, we have the first is the kinetic Hamiltonian, and the second term is the problem Hamiltonian or potential Hamiltonian. And the potential Hamiltonian can be expressed into this Ising form. Yeah? So we have the first term is GIG, sigma I, sigma G, and the second term will be HI, sigma I in Z direction. And the driver Hamiltonian or the kinetic Hamiltonian will be can be expressed into minus gamma sigma I hat X. So this is the X Pauli matrix. And we have done various experiments from finding smaller Hadamard matrix. And then we also consider several experiments related to Hadamard matrix. And before going to the detail of the experiment, first I will explain briefly the D-Wave 2000Q that we use in this research. The D-Wave 2000Q has 2048 qubits, and they are connected by 6016 couplers, and the topology of the connection is chimera graph. The chimera graph, the structure of graph is something like this one, which is a bipartite graph, a bipartite complete graph of order 4, 4. This is the unit cell, and they are connected also by couplers to other groups of the qubits. So what we have to do is this one, D-Wave. We use the D-Wave which is provided by D-Wave Corporation in Canada, and we input our data through a notebook or a personal computer, and they provide a graphical user interface to enter the data, and then by using cloud, we send the data into this computer, and then the quantum annealing is run in this computer. In the first experiment, we want to find 2 by 2 Hadamard matrix. Therefore, we have this kind of Hadamard matrix, and S0 up to S3 are matrix elements that we want to find. Then we can calculate the energy of this matrix of this problem by multiplication of the matrix with its transpose, and we have this kind of elements in the matrix, but we can simplify. So the D, the indicator matrix, will be like this one. So the first elements, D11, with the simplification of these terms. We know that S0 by multiplied by S0 and plus S2 by S2, S0 will be minus or plus 1. Therefore, their product are square, and it will be 1, and the second one also similarly done, and the value will be also 1. Therefore, 1 plus 1 we got 2. We can do similar analysis to these elements, D 2 by 2. So S1 square plus S3 square will be equal to 2. And the remaining part is the off-diagonal elements, and it contains the variables S0, S1, S2, S3. And because they are asymmetric, we can only consider the upper part of the D, upper diagonal terms of the D. Now we know that the energy is the off-diagonal entries square, so we perform the square of these elements, and we get, after simplification, we get this 1 plus 2, S0, S1, S2, S3 plus 1. Therefore, we can collect the constant into 2 and the remaining variables, like this one. Well, this is the 4 body interaction. So, as explained before, we have to convert to up to 2 terms, 2 body interaction. So, after substitution, after transformation that explained before, we can get this A to S display in this part. And as we can see here, we have now we need 5 variables, 5 spin variables. the highest index of this variable is 5, therefore we need 6 variables. And after transformation, we get this equal, so we just replace s with sigma, etc., sigma z from 0 to 5 here. And we can translate this one to the G, which is matrix of containing all of the Ising equation, Ising model. Yeah. So because this is also symmetric, we only display the upper part diagonal of G, and this is the each part, which is 1, 2, 3, 4, 5, 6, 8. So this is the its coefficient, and after we obtaining this G and H matrices and vectors, we can encode it to the D-Wave. So we submit by using our terminal to cloud, and it is then sent to the D-Wave 2000Q. Okay, so we continue with this analysis. What happened in the D-Wave 2000Q? This coefficients, this Ising coefficient G and H, will be translated into a coupling strength between the qubits. So we encode this coefficient into this qubits, and because this one we only have a few qubits needed in this coefficient, then we can manually write assign the qubits, which qubits that we want to use, and the strength, the coupling strength among the qubits. And after finishing encoding the strength of qubits into the D-Wave processor, we can execute the quantum annealing. So we just adopt the default annealing schedule, something like this one. So this is increased, and this one is decreased. The kinetic part of the Hamiltonian is decreased, and the potential problem Hamiltonian will be increased. And after finishing this execution, we get this this graph. We get this bar chart showing the distribution of energy against the solution indices. And this one is the occurrence, and we can see clearly here that the lowest energy has a high distribution. So we can forget the other solution, and we just check this one and check whether the matrix or matrices to order Hadamard matrices found or not. And we can see here that we successfully found this Hadamard matrix. So by considering plus is equal plus 1 and minus is equal minus 1, we can verify easily that this 2 by 2 matrices in fact are orthogonal. So the next experiment is finding for order Hadamard matrix. For order Hadamard matrix needs 4 by 4 or equal to 16 spin variables. But again, we obtain 4 body interaction, and we translate it into 2 body interaction, and then we can get the H2 sigma, or the problem Hamiltonian, which consisting of 389 terms, and the required qubit numbers is equal to 40. And as we can see here, because we have so many terms in the Hamiltonian, we need to do it automatically by using symbolic computing. Okay, then as done like in the 2 by 2 cases, we have to encode the coefficient of this Hamiltonian into the coupling strength between qubits in the D-wave. So actually it is done automatically. There is a utility in the D-wave that translates the coefficient into the connection between qubits and the strength of connection among them. Okay, so this is the total map of the qubit, and our problem now we have this area. So our problem is mapped into this part of the qubits in the D-wave. Actually, it's about 1/4 or less, a little bit less. So after execution of quantum annealing algorithm, we can have distribution of the solution, something like this one, similar with before. And after extracting the value of the qubits after observation, then we can find the solution, and actually it is found. So we can verify here that this is the found solution by using quantum computing, which is implemented in the D-wave. Next, we did experiment with finding 3 orthogonal 12-length vectors. So we observed before that the qubit used in the previous problem, only about 1/4 of all qubits are available in the D-wave 2000 and Q. And we want to try higher number of qubits, but if we try to find the next order of Hadamard matrix, which is 4 by 4 and 16, then it is not sufficient. So we try another problem, and in this case, we have 72 variables with 7,765 terms, and after embedding, it needs about 1,766 qubits. So because we have 2048, most of the qubits now occupied or used. Yeah? Most of the qubits are now used, and we can see here in the blue area, almost all of this area are blue. Okay, after execution with a quantum annealing in the D-wave, we can get this distribution of energy and occurrence. And after extracting the value of the qubits after measurement, now we can get there were 1,000 D-wave answer, where 635 was wrong and 365 were correct. And this is the example of the correct answer. And finally, we did the experiment for finding one vector which is related from the Hadamard matrix of order 12. So we did one, then we provide 11 of the vectors displayed here. And actually, this is rather a simple problem, and actually it is only required a few number of qubits displayed here. And after some computation, we get H2, the problem Hamiltonian consisting of 38 variables. Sorry, this is 38. 28 H variables, 379 terms, and after embedding, we know that this problem needs 50 qubits. Okay, Then again, we did the quantum annealing, and there is only two solutions we can observe here, and actually both of them are correct. So the solution distribution is something like this. This one is higher than this one, but the number are after summing the probability, they will be equal to 1. And one of the solution is listed here, V11 equal minus plus minus minus 3 plus and minus plus plus minus. And if you put into this set of orthogonal vector, you can verify that actually this one is the solution. Okay, as we see here, we have two solutions. This is one solution. So what is the other solution? We found that the other solution is the negation of these vectors. So instead of minus, this one become plus, minus, plus, 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 etc. And it is also a correct solution. So we have done all the experiments, and we have successfully found the Hadamard matrix, the quantum computing can solve our problem. And what next? Okay, so after solving all of the problem by using DWAVE 2000Q, which has 2048, we realized that it can only find low order Hadamard matrix, which is the highest one was 4 by 4, and although we have a large number of qubits, this is insufficient for high order. And so what next? So we need a qubit efficient method. So in the following paper, we successfully found this method. We adopted classical Hadamard matrix search, and we do some computation. We convert the equations into new quantum computing algorithm. This concludes my presentation. Thank you.